Yes, Kutu sir has also joined us. So let's start. So, first of all, welcome to one and all. All of you are welcome to US Space Club webinar session 56. To talk about our webinar series, we started our webinar series when the world were stuck due to the COVID pandemic issues. All our activities were also paused due to the restrictions and guidelines given by the government. We were unable to conduct space camps and other offline activities. So we started a webinar series with an intention to conduct just like a 6 to 10 sessions, something like that. But the response we got from students and our mentors were amazing, and we
Varun, are you stuck? Varun,
I think
any
Varun
connecting?
is stuck.
Oh,
sir,
great.
sir,
Okay,
sir,
okay, you continue. Okay, you
Varun has
continue.
come back. Varun has come
Okay,
back. Okay.
welcome, welcome.
yes, sir, yes, sir. Sir, we are on the 56th session of our webinar series now. Today we are an interesting topic, which is a modern technology used in space science and technology field, and we have the lead professional from ISRO to talk about that topic, because she is the project director of this particular project for ISRO, and we have Dr. Manju Nair from LPSC, Liquid Propulsion System Center of ISRO here. I just met her during the Professional Student Summit at Angamali Atlas Convention Center, Angamali. It was a program conducted by Government of Kerala, and I was lucky enough to attend her class. And after that, I just connected with her on behalf of UL Space Club. And I got an opportunity to interact with her. So after that, I contacted her by talking about our webinar series, and she was very happy to join hands with us. And he was ready to give a session on electric propulsion. So today we will have a talk on electric propulsion for space in the leadership of Manju ma'am. So you can have queries during the after the session, after the presentation of our speaker. You will have a question answer session, and for that you can type your questions in the chat window during the presentation of our Manju ma'am. So you can we will select your questions and you can answer you will get the answer at the question answer session time. And after this particular question answer session time, after vote of thanks, we will post a link of a quiz, webinar quiz, which will be based on electric propulsion, completely based on the things that will be shared by Manju ma'am on this webinar. So we will have a quiz. All of you are requested to attend the quiz, and there'll be a small prize for the first prize winner. So all of you try to attend that quiz also. So once again, welcome to one and all for the exciting webinar session. First of all, we are very happy about the presence of Manju ma'am here. Thank you, ma'am. So let's welcome her. And for the introducing our speaker in detail, I will welcome our Shajil sir, who is our mentor and a teacher. So I welcome Shajil sir to introduce Manju ma'am.
Okay, okay, thank you, Varun. The UL Space Club, a prominent student-run organization and dedicated to promoting space science and technology, is proud to announce its 56th webinar on the topic electric propulsion for space. And we have conducted 55 webinars so far, but from this webinar session, we are adopting another innovative method by which we are making a co-host in this program. Today we have the co-host, the Spring Valley School. It's situated in the NIT campus under the management of NIT personnel there, NIT Calicut, and there are a lot of enthusiastic space students there. And the principal is Shiny is there representing Spring Valley School here. And the former director ISRO, E.K. Kuti, is the founder of this UL Space Club, is also joined with us. And we are awaiting to hear a special topic that's about the electric propulsion in the space. It's a new area for that. We are in search of the energy sources. That is the only sun we have, and we are still to utilize the energy there. And and the other thing is that using electricity, we are using these kind of propulsion techniques. That's a novel era in the space explorations. Anyhow, today we have a great scientist from VSSC, Dr. Manju S. Nair. Let me introduce her, today's speaker for you. Manju S. Nair has been with Liquid Propulsion System, LPSC, in Indian Space Research Organization ISRO since 1998. She is currently as a senior scientist, and she is an alumnus of College of Engineering Trivandrum and received her doctorate degree from the Indian Institute of Science, Bangalore. She is pursuing her research activities for electric propulsion system, which can replace chemical propulsion system in spacecraft and also control electronics for launch vehicle systems. She is now the project director for the high thrust electric propulsion system for the project of ISRO and is responsible for developing, delivering various variants of electric propulsion system for ISRO satellites. She also heads the electronics design division of LPSC, leading the activities for development of highly efficient power control packages in the electric propulsion system and also miniaturized control electronics for the first stage of Polar Satellite Launch Vehicle (PSLV). She has received the award for Team Excellence in the field of electric propulsion. She has also published many technical papers in international journals. So we are proudly presenting and introducing Dr. Manju S. Nair to this forum. And again, we are welcoming our co-host, Spring Valley Schools, and that is being represented by Ms. Shaini, the principal of that institution. Before we are going to our wonderful talk, I invite Mrs. Shaini to make a presidential address in this gathering. And I invite all the dignitaries of the veteran scientists and the teachers and students who are gathered here, including our founder, E.K. Kutisa. In this forum, I invite Mrs. Shaini to make a presidential address before our talk. Welcome, ma'am.
Thank you, sir. Respected dignitaries of today, founder and mentor of the Space Club, Sri E.K. Kuti, moderator, Sri Shajil sir, resource person of today, Dr. Manju S. Nair, students of various schools, the learned minds in the field of science from different parts of our country, the mentors and the others present here, a warm good evening to one and all. It is indeed a great privilege for me to address this august and enthusiastic main gathering on behalf of Spring Valley School. To be a part of this family is an invaluable opportunity for us. And to talk about my school, as Shajil sir said, it's functioning in NIT Calicut campus. It's managed by REZ Spectra. The members of this society are the faculties of NITC. And let me first extend my gratitude to Dr. Prasad Krishna, Director of NIT, for paving a path for us through Shajil sir to UL Space Club. Shajil sir and Kuti sir, thank you so much for this. And all the students present here today might have attended all those 55 webinars held. But for my school, this is a novel experience. And the aim of this club is to develop an attitude and aptitude of science and making students ask why and why not. I believe that this particular question, why, is what leads to creativity. And this question, why, creates innovative thoughts. That's what I think so. And these children get a lot of learned minds to coming to them and talking to them, and their experiences, clearing out their doubts and all that. And I think this opportunity should be used very, very creatively by the students, and hope so all my kids would do the same along with the other kids. And today's resource person, Dr. Manju S. Nair, is here, as we all know, to talk on electric propulsion for space. This session, I hope, is going to be very informative and thought-provoking for all the students present here. And my advice to the students is to take this opportunity in molding their minds with great lessons that they would get from here for the sake of humanity and the planet in itself. And so, with this humble words, I would like to thank each and everyone over here and we are waiting for this great session. Thank you all. Thank you, Shajil sir.
Okay. Dr. Manju has said to present her wonderful and interesting speech in this forum. And I invite all of you to listen to that. And students will get their chance to ask the questions, and that will be discussed later. Okay, welcome, ma'am. Manju, please. Manju, ma'am, please unmute your mic. Okay, okay, ma'am.
I'll first share my presentation.
Okay, ma'am. Okay.
Is it visible?
Yes, ma'am. Yes.
Okay, can I start?
Yes, ma'am. Sure.
Yes, ma'am. It's okay. It's visible. Please make it a full screen mode. That would be better.
It is in full screen mode only.
Okay. Thank you. Thank you. Thank you.
Okay. So first of all, good afternoon to all the dignitaries and the students present here today. I'm so happy to address. Pardon?
No.
Good afternoon, ma'am.
Good afternoon.
Okay. Adil, please be there. You will get the chance to talk. Okay, then only. Okay. Please.
So I'm so happy to address the student community, and I'm so excited to talk to young generation, because I always felt that they are so fresh and like a sponge to absorb all the new things and curious as ever. So I'm really excited. I'll try to answer all the questions which they have. If not, also I will reach out to them separately. So with that, let's start my topic, electric propulsion for space. So as said in the introduction, I am currently the project director for this project for ISRO, which will supply the various variants of electric propulsion system for the different spacecrafts of ISRO. Oh, sorry. So my content is organized like this. First, I will start with some basics, why propulsion is needed in satellites and why electric propulsion. Also, I will tell you some advantages, applications, and challenges involved in the development. And I will also tell you some pioneers, because students are involved. I incorporated these also, some pioneers and some major milestones in the development activity. And also different types of thrusters are there. So I will tell you all about that. And also this involves a different kind of testing altogether. It's not like chemical thrusters. So how will we do the testing? I will tell you about that also, and what the future is in store for electric thrusters. So first, we'll start with why do satellites need propulsion? As we know that when we put some object in some orbit, on a specific orbit, it has certain velocity and it goes on circulating in that particular orbit. Then why on earth do we need propulsion? So there are some specific needs why propulsion is needed. First is change in velocity. Suppose that the satellite, we are talking about satellites now. So satellites are in specific orbits and it is going on orbiting in that orbit. And suppose there is a need to change the direction or the speed. For example, you are all aware there is a lot of space debris in different orbits up above the Earth. So in case of collision, we want to avoid the collision. We want to change the direction. That times we have to fire the thruster. And further, if we want to point it precisely to some object, some celestial bodies or something, then also we need to fire thruster. I'll come to that. So second is attitude. As I told, the attitude of that satellite should be precise, so that it. So see
the presentation hasn't changed. The slide hasn't changed.
Oh, sorry, it has not changed.
No.
I'm in second slide now.
Ma'am, it's in the first slide now.
So what should I do now?
Yes, sir. Now it has changed. Now it has changed.
Actually, now I'm not in presentation mode. Is it okay for you?
Yes, ma'am. Yes, it's okay, but
it's okay. But I think it's not in the full
yes,
screen mode.
It is not in the
yes.
Yes.
Okay, please put the F5 or put into the full screen mode. Like, that would be better.
Now, am I in the third slide?
Yes, ma'am.
Yeah,
Yes.
it's in the, yes, why do satellite need propulsion? That's it.
Okay. So I explained now change in velocity. Now I come to attitude. See, the satellites have specific purposes. Some are for observation purposes. They will be that we have some observatories in space, so they require precise pointing to maybe sun or some other bodies in space, or maybe the Earth even. So that amounts to precise pointing of the satellite. So then we have to fire these thrusters and precisely control the attitude of the satellite. There also propulsion is needed. So for maintaining the orbit, here also for communication purpose or for navigation purpose, we need to maintain the orbit always. So we have the north-south station keeping and east-west-south station keeping. For all these, the thrusters need to be fired, and hence propulsion is needed. Then we have some specific orbit maneuvers. For example, if you want to put a satellite in geostationary orbit, it may not be always possible to directly go to that geostationary orbit because it is in 36,000 kilometers away. So what we'll do is we will put in some elliptical orbit and we'll fire in apogee and perigee and we'll raise that orbit. Sometimes we'll put them in GTO orbit, that is geotransfer orbit, then we'll raise to stationary orbit, like that. So for all this, propulsion is required. Finally, for interplanetary travels, definitely we require longer time, because it will take longer time to reach our in other planets. So hence propulsion is needed there also. Now, to understand some of the things I am going to elaborate in the coming slides, first we'll understand what is rocket equation. So in the first slide, at time t is equal to 0, we can see that the satellite or the spacecraft, it contains both the mass of the rocket or the satellite and the fuel, and it has a certain velocity v. Now at time t equal to delta t, the fuel has burned and it has come out with a certain velocity, that is C exhaust, and it has imparted a certain velocity to the body of the rocket or the spacecraft.
Dr. Manju,
Yeah?
please change the slide.
I have changed the slide, sir.
Now it has
Now
come.
it has changed.
I
Ma'am, at
think-
right bottom corner, you will have an option to increase the size of your slide.
I think there is some issue when I change the slide. Otherwise, I think now.
Now it's enough, ma'am. Please continue.
So I think when I change the slide, I have to go out of that mode and I have to come back again. That's what I'm saying. Okay,
Okay,
Manju.
ma'am. Please continue.
Continue.
Just tell me, because I am not aware of that. Just tell me when the slide is not changing.
Ma'am, I think while clicking present option, click your entire screen. I think it will solve the problem.
Okay, then shall I do that once again?
Okay, ma'am. Please try.
Yes,
I will try that.
possible. That's
Just excuse me, I will do that. Is my screen visible now?
Yes, ma'am.
yes, ma'am. It's visible now.
Rocket equation is
yes.
seen?
Yes,
Yes,
it's
yes.
fine. It's fine. It's fine.
Okay. Just tell me if the slide is not changing. Okay. So this is the rocket equation, and I'll come to the equation. So this equation was coined by Solkovsky, a Russian scientist. And here we can see the very important relation between the delta V, that is a change in velocity of the rocket or the spacecraft, to the exhaust velocity. And again, it is a relation, a logarithmic relation between the mass of the rocket and fuel to the mass of the rocket. But here what we are interested is the relation between the delta V and the CS. So you'll understand why I am stressing on this in the future slides. Can you see the slide? I have changed it.
Yes, it's okay.
Okay. So now why we need electric
Yes,
propulsion?
ma'am. Yes.
Okay, thanks. So why we need electric propulsion? So suppose you want to take a mass of 1000 kg to moon with a delta V of 16 km per second. So in this case, we will do a mission analysis and we'll come up with something like this. So I have taken this from a paper, and you'll understand very easily why or what is the importance of electric thrusters. Here we can see that if suppose a solid rocket is used for this mission, we have to use some 600 tons of solid rocket. And for if we use a liquid propellant, it will be 147 tons. For cryo engine, it will be 34 tons. But if we come to the last three options, which is the electric thruster class, you can see that the mass has drastically come down around 400 tons or below that. So this is why, because I've told in the earlier rocket equation, the exhaust velocity is so high. That is why we can drastically bring down the propellant mass. So definitely for such a mission to Moon or Mars or interplanetary missions, electric thrusters will be preferable than the other thrusters. So I will be explaining on Hall thruster and ion thruster in the coming slide. Vasimer I have not put. Vasimer is nothing but the propellant will be thermally, it will be heated up by RF frequency and it will be ejected out of the thruster. Is it okay? I've changed the slide.
Yes, ma'am. Yes.
Okay. So now this is a summary of electric propulsion and chemical propulsion. As I already explained, chemical propulsion basically relies on the combustion of the fuel, and hence, if you want more energy from chemical propulsion, you want more fuel to be stored. But in the case of electric propulsion, there is no fuel. Yes, there is a propellant, but we are not depending on the combustion of that propellant. We are actually depending on the electrical energy, and hence it is power limited. It only depends on how much power you can generate in the satellite. And here in chemical propulsion, we are talking about exhaust velocity in the range of around 5 kilometer to 6 kilometer, wherein in electric propulsion, we are talking in hundreds of kilometer per second. And in chemical propulsion, we are burning a big amount of fuel in a very short time, hence we get high thrust. Maybe you have all heard of this Artemis mission. Now NASA has recently launched, and there actually the amount of lift of mass is around 2000 tons. So in that huge amount of thrust, we can only rely on chemical propulsion. But the advantage of electric propulsion is that even though the thrust is very, very small, it can last for longer time because the efficiency is very, very high. So this is a comparison of chemical and electric propulsion, and it all depends on the mission planning where to use what. And here I have put a last line. Suppose you have some fixed payload, and if you want to use that in a 5.5 ton class CPS satellite, that is chemical propulsion satellite, it can be directly converted into a 3.5 ton with the use of electric propulsion. So that is the advantage of electric propulsion over chemical propulsion. Now, some other advantages other than what I have stated is that it is simpler in design. So it brings out cost effectiveness in the thruster implementation. And further, there is no moving part in an electric thruster compared to the chemical thrusters. So there is no repairability is involved. So hence more reliability. Again, as I told, there is a thing called ISP. All the ISRO people here knows there is a term called ISP, which actually denotes the efficiency of the propellant used in the thruster. So here the efficiency is very, very high in the range of 2000, 3000 seconds. So the lesser fuel is consumed here. That is the biggest advantage of electric propulsion. Also, no fossil fuel or no hazardous gas is emitted in the electric propulsion. So that will also lead to environmental benefits. Now, because it's a student community, I just want to introduce you to some giants who have done some great work in this field, and that's why we are standing where we are now. As the phrase goes that we stand on the shoulders of giants. So these are some pioneers in the electric propulsion. Solkovsky, who is the made that or coined up that rocket equation, as I told. So he was also one of the first persons who brought out the concept of chemical rockets. He was a Russian scientist, and he was closely followed by Goddard. He was an American scientist, and Goddard is called the father of modern rocketry. Even though both of them has done great work in chemical propulsion, they were also the proponents of electric propulsion, and followed by Kondrayev and Obert. The interesting thing is that even though all these 4 people have done great work, Solkovsky, what he has done is known to only a few small circle of people around him. And Goddard, actually, he had written down all the findings in his personal records, and we came to know it very much later. Conrad also is less known, but Oberth has made or released a book on this, and it is regarded as a Bible in electric propulsion. And Glushko is actually a pioneer in Soviet space program. Now, these all giants, they worked from 1906 to 1956, that period. And after that, actually, there are a lot of implementation of this technology. And it started from 1957 with CERT-1, which was the Russian attempt on with ion thruster. They started with the ion thruster. Sorry, the CERT-1 was American, and they started with ion thruster. And then in 1971, Meteor 1 was done by Russia with SPT. And 1998, Deep Space 1, the year I joined ISRO, they have done Deep Space 1. And 2003, Smart 1 mission was done. Smart 1 is particularly unique because it was a moon mission, and here the primary propulsion was electric propulsion. That was the uniqueness of Smart 1 mission. And 2001 Dawn mission was done. This was an asteroid mission where B-Span series 2 asteroids were actually investigated by this Dawn mission, and here also ion propulsion was used. And in 2017, ISRO has done a electric thruster experiment in GSAT-9. And we have actually, we didn't have the technology to make thruster at that time. We have brought the thrusters from Russia, but we had all the other EPS technology we have implemented indigenously. And they have flown in GSAT-9, and for 1 year, this was successfully operating in orbit for north-south station keeping. And finally, I have not put all the milestones here due to lack of space. Only the major ones I have put. And in February 2023, SpaceX has launched Argon thruster in Starlink's V2 Mini, and there are some 21 satellites they have experimented with this thruster. Now, coming to some of the applications, I've already, you might have got an idea how useful it is. But even though in communication satellite, because we require, you know that communication satellite always point to a particular point in the Earth, always for communication purpose. So that for that kind of application, electric propulsion is very much helpful. And for deep space probes, because they go to longer distances, they take longer time. So higher fuel efficiency and higher efficiency do matter there. And for all the scientific missions, I have pointed out some of the scientific missions, but there are so many other scientific missions like Bepi Colombo, which has explored Mercury. Then some NASA observatories there which observe Sun. So many scientific missions have been done with electric propulsion. Then also there are so many emerging technology in electric propulsion like gridded ion technology, zero erosion technology. So all this can be technologically demonstrated using this kind of thrusters. And as I told already, the orbital maneuvers can be done precisely using these electric thrusters. And cargo resupply, now we are relying on chemical propulsion for the cargo resupply to ISS and all that. We can rely on electric thrusters because it is less expensive also. Also, when it comes to high delta V applications like moon mission or Mars mission or Jupiter missions and all that, we can use electric thrusters compared to chemical thrusters. And as I told, it is very much because it's the thrust is very, very low. This firing of thrusters can be precisely controlled. So it can be used for all the kind of scientific missions and all that where high precision is required. Now I'll just explain how this electric propulsion system works. Basically, I have put in only the general description here. Then I'll come to the different thrusters wherein how this phenomena is implemented in the different thrusters. I'll explain. Now, basically, in electric propulsion system, unlike the chemical propulsion system where the fuel is ignited, it will actually in a chemical propulsion, how thrust is generated means the fuel is ignited and it will be expelled through a convergent divergent nozzle. Thereby, it will impart the thrust to the thruster body and thereby the rocket or the satellite body. But here what happens is that some charged particles are generated, which we call plasma, by some means. And that is accelerated by either by electric field or by magnetic field or a combination of both, which then imparts this kick or the thrust to the thruster, thereby the satellite or the satellite body. Here, rocket is not involved. Now, because these particles are very small and because we are accelerating with high electrostatic fields and all that, the speeds we achieve is very high. And we know from the rocket equation that since that they are in high speed, the delta V is very, very high. Now, since we know that the particles are very, very small, like ions and electrons are only involved, the thrust is very small, but it gives a very steady thrust for a longer time. Now, the problem is that there are a lot of charged particles outside the satellite. Everything is going out and it's a cloud of particles sitting on the spacecraft. Now, if this cloud of particles, charged particles, if they impinge on the spacecraft systems, there are so many sensitive systems on the spacecraft. Even the solar panel, it can damage the system. So what happens is that there should be a neutralizer system which is available outside the satellite to neutralize all this charged particle. Okay, so this is a basic idea for all the thrusters, electric thrusters. Now, I told about plasma which is generated, and you know, you're all will be aware that it is a fourth state of matter. And it is 99% of the matter in the universe is plasma. You'll be surprised to know that because in Earth, it is the rarest of matter. Because most of the stars, even the sun, it consists of plasma. That is why 99% of the matter in the universe is plasma. Now, we have some man-made plasma like our neon lights and fluorescent light bulbs and all that. So this will give you an idea. Because when we think of plasma, we always think of high temperature, but that is not the case. It varies from case to case. Like, for example, in aurora and even in the flames, when we lit a candle, there is plasma inside, but the temperature is very low. But if we take the case of solar core, or even the lightning, the temperature is very high. So these are some of the examples I just got from net to give you an idea. So coming to the different types of thrusters, the classification is based on how the ions are expelled out of the thruster. So we have electrostatic thrusters, electrothermal thrusters, and electromagnetic thrusters. So electrostatic thruster, mainly they use a high potential to accelerate the ions out of the thruster. So we can see ion and SPT. This is an ion thruster and this is a SPT thruster. SPT means stationary plasma thruster. Mainly, excuse me? So ion thruster, mainly US was making ion thrusters, and SPT was made by Russians, but now US also gradually moving on to SPT because they are highly efficient and less power hungry. Now coming to electrothermal. In electrothermal, basically the propellant will be heated and then they'll be pushed out of the thruster. So arc jet and resistor jet, this is the arc jet thruster we are seeing on the photograph. So that is how the thrust is generated. Now in electromagnetic, basically the magnetic field will generate the Lorentz force, and that is how the ions are expelled outside. And some examples are given: magnetoplasma plasma dynamic thruster and pulse plasma thruster. I will come to that in detail in the following slides. So this is an arc jet. So I hope you can see my mouse. This is a cathode, which is a pointed one. This is the cathode, and the body of the thruster is the anode. Now, how arc jet function is that there will be an arc struck between the anode and cathode. So this arc will generate high heat, and the propellant will be admitted to the backside of the thruster. Now, because of this arc and because of the high heat generated by the arc, this propellant will get heated up. Now, it will be ejected out of the thrusters through a convergent divergent nozzle, and thus the thrust will be imparted to the thruster. So resistor also operates in the similar lines, but here instead of the arc, there will be a resistive element, a heater, and the propellant will be admitted to the backside. Now the heater will be heated by supplying a high current, and because of the heat generated here, the propellant will be heated up, and here also there will be a hot gas exhaust, and thrust will be generated. Now coming to magnetoplasma dynamic thruster. Here how it is done is that this is the cathode, the pointed cathode, and body is the anode. Now here propellant is admitted likewise from the backside of the thruster. What is done here is that between the cathode and anode, a high current is given. So this high current actually ionizes the propellant, neutral propellant here, and it generates a plasma. Now a magnetic field, you can see the circle here, magnetic field is established here, and because of the presence of the electric field and a magnetic field, J cross B, that's a Lorentz force, which it will actually expel all the ions out here, and thereby the thrust is generated. So here usually some argon is used as propellant. Now PPT is pulse plasma thruster. It's a slightly different technology. Here we can see the anode and cathode are placed here, and here a solid propellant, mostly PTFE or Teflon is used. And what happens here is that between the anode and cathode, a high voltage is given, and this solid propellant, it is sublimated into plasma. Now plasma, as we know, is a good conductor of electricity, and because of the availability of the potential here, a current start to flow through this plasma. Now there'll be a magnetic field, and there's an electric field already existing. Now here also Lorentz force is there, and so it will expel all the ions outside the thruster, and then it creates a thrust. Now coming to our main ones, like the ion thruster and plasma, SPT thruster. Now ion thruster, ion plasma, stationary plasma thruster works differently from the other thrusters which I have explained so far. Here, what happens is that this is a thruster body, and we have an electron gun at the back of the thruster, which continuously generates electrons. Now, the green color spherical balls are the neutral propellant atom. So that they will be admitted also from the backside of the thruster. Once they are present together in this area, what happens is that the electrons strikes these neutral propellant atoms, and they will be ionized. Now, positive ions are present here along with the electrons. Now we can see the cross section of magnets here, so that will create a magnetic field which will direct these positive ions and electrons to this area, to the outside of the thruster. Now what happens is that because of the presence of this negative grid, which is put at a higher potential, and because of the pressure of the propellant, which is continuously entering the thruster, all the positive ions will be attracted to this negative grid, and they will be actually accelerated out of the thruster. So that imparts a thrust to the thruster. Now, as I told earlier, because this positive ions which are present outside the satellite or the thruster should be neutralized, so there is an external cathode or an electron gun here, which actually neutralizes all the positive ions. So we can see the artistic depiction of what I had told. These are the positive ions, and the electrons are there, which neutralizes the positive cloud. Now coming to the stationary plasma thruster, which was used earlier by Russians, and now ISRO is also doing this technology. Here you can see it's slightly different from ion thruster. Here also we have a back plate where the propellant is admitted, neutral propellant is getting admitted, but it also works as an anode plate where we apply a high positive potential. Now the cathode is situated outside the thruster, nearby to the, here this is a discharge channel, so the cathode is outside the discharge channel. So the basic structure of cathode is that there will be a thermionic emitter inside the cathode. Now, for the thermionic emitter to work, it should have thermal energy. So we have a heater outside the thermionic emitter, and high current will be passed through that heater, which heats up this thermionic emitter. And thermionic emitter, basically what we use in SPT is tungsten impregnated with calcium, aluminum, and boron. And now what happens is that the electrons will be emitted from the that emitter material. And now here also we are admitting the propellant into the cathode. So a plasma is generated. Now these electrons will come out of this cathode. Now, since we have applied a high potential at the anode here, this electron will see this high potential and it will rush towards this high potential. But by that time, we would have switched on the magnetic field. Now, what happens is that the electron which tries to rush to that high electric field, it gets entrapped in this magnetic field and it will undergo cyclotron motion here. Now, since here also electric field and magnetic field are present at 90 degree, what happens is that Lorentz force J cross B exists. And now what happens is that the propellant molecules which are coming from the backside, they will reach here. Then they will find these electrons here and they will get ionized. Now, because of the Lorentz force already existing here, these ions will be expelled out of the thruster. So this is how the thrust will be generated in SPT. Here also, this cathode has a dual purpose. It will actually supply the electrons for the ionization purpose, and it will also supply electron for the neutralization of ions outside the thruster. So this is the artistic implementation of the SPT firing. Now, as we told that the thruster can fire forever, depending on the power and all that. But is it so? It is not so. There are some life-limiting processes also inside the thruster. What is it? First is that in the anode, here there are some liners here. So this basically boron nitrate with silicon oxide. Some liners are there. This is to protect the poles, electromagnetic poles of the thruster. Now, what happens is that because of the operation of this ion thruster, these ions and electrons get impinged in this anode liner and they will slowly erode over time. What happens is that then the magnetic field, the shape of the magnetic field will be different, and we will not get the correct Lorentz force and the kind of operation we are expecting from the electric thruster over time. So next is a cathode. As I told, there's an emitter material, and the emitter material has to emit the electrons, and it all depends on the emittivity of the cathode. So it also has a life. So we have tested for some 5,000, 10,000 hours, but more than that, it will affect or limit the life of the thruster. Now, I just put in because it is very interesting for the students here. USEC is a private party. They are in US based. They have actually experimented with different kind of propellants. What commonly used propellant is xenon. ISRO has used xenon only. Russians also mainly use xenon. So we can see the beautiful blue flame here. So here, but when we go to other the propellants like zinc, bismuth, krypton, iodine. See, the iodine is having a green plume, argon, magnesium. So I have told about SpaceX, and they have used argon now. So this may be the plume they have seen. So magnesium. So these are all the different kind of propellants they have tried out. Also, I want to thrust upon the fact that why we are using SPT. Why we means ISRO. Because as we can see the statistics here from 1960 onwards 2019, the red is Hall thrusters alone, and violet is all the thrusters combined. So we can see over the years the usage of Hall thrusters has increased, and by 2019 you can see that it's almost matching with the combined use of all the other thrusters. So everyone is gradually migrating to thrusters, and we are also experimenting on different kind of thrusters as part of our project. Now, coming to the power levels also, we need to understand what is or how much is 1 millinewton. Suppose we blow the air on a paper, that much thrust is called 1 millinewton. So even to generate that much of thrust, that is 1 millinewton, we require 20 watts of power. So that is a thumb rule. So you can just understand when in 1980s or 1970s, the power was generation was around less than 500 watt or so, and it has come to 5,000. But 5,000 watt means we can generate approximately around 300 millinewton of thrust only. So this is the problem of electric propulsion, because we require a huge, enormous amount of power to generate the high thrust. But But over the years, the generation power of the spacecraft has increased to 5,000 watts. Now, coming to testing, as we know that chemical propellant can be tested in ground condition, but here the vacuum is very, very important, and we require around 10 raised to minus 5 millibars of vacuum. So we have special vacuum chambers, and I have not put all the photos. We have some additional chambers also. So we are testing in this kind of special chambers. And also we have a thrust measurement system, because thrust measurement system is very, very important. As I told, when we make a thruster, when we test it, it is very important to know the thrust, then only we can finally plan the mission. So thrust measurement system is actually a very complicated system, and it is made by only a few players in globally. What they actually do is they will hang the thruster inside the vacuum chamber, and whenever the thruster is fired, as I told, the movement is very, very, very minimal, and that will be sensed by some sensors, and that will be converted to thrust. So whenever we are doing the testing with the thruster, we always measure the thrust, and then only we can evaluate the performance of the thruster along with so many other parameters. So as I told you, thrust measurement is a major criteria for testing the thrusters. Along with that, there are so many other things. We need to identify what are the elements in that plume and how it diverges. For example, for a typical SPT, the plume divergence angle is 40 degrees. So if the plume is diverging more or less, it will create a problem, or it will come to know the efficiency of the thrusters. So we need to analyze all this with a multispectral image analyzer. And also we need, as I told, the erosion is very, very important. We need to, that actually is directly proportional to the life of the thruster. So the estimation of the erosion of the ceramic liner is done by the optical emission spectroscopy. Also, we need to know what are the high frequency elements present in the thruster. Actually, these thrusters, particularly the SPTs, this had a breathing mode oscillation in the around the range of 25 kilohertz. And it has certain harmonics also. So we need to find out what are the harmonics present in the thruster. So they all will be done with FFT using high-speed data acquisition systems. Also, we have different diagnostic probes like Langmuir probe. It is a 1 to 2 mm tungsten probe. Pardon? Excuse me? Am I audible? Hello?
Yes, you are audible.
Okay. Okay. Thank you. So Langmuir probe is a small probe which is around 1 to 2 mm length. What we do is actually is made of tungsten. It will be put into the plume of the thruster, and it will be biased. So actually plasma is also highly conducting. So there's a difference of potential. Then there will be a current through the probe, and this current will be measured, and then we'll come to know the temperature of the electrons present in that plume. Similarly, Faraday cup probe will actually collect all the ions, and we'll come to know the ion beam intensity in the plume. Again, retarding potential analyzer analyze the energy distribution over the plume divergent. And also the E cross B probe. It actually measures the velocity of the ions at different points in the plume present in the thruster. Also, electrostatic analyzes the energy, mass, and charge distribution of the plume and its impurities. So these are the different kind of diagnostic probes. We are actually, ISRO is now developing it indigenously. Earlier we used to buy, now we are developing it indigenously. Now coming to specifically to the developments in ISRO, as I told before, we are in line with the worldwide trends. Initially, we didn't have the technology for developing the thrusters. We used to buy from Russia, but now everything is indigenous, including all the materials. We have some special adhesives, etc. we used inside the thruster, and special materials are used. All that is indigenized now. And these are some of the photographs of the thrusters we have made here. This one which I am pointing to, this is 300 millinewton thruster. This one is 75 millinewton thruster, and these are the cathodes which I have earlier told you about. And this is our indigenous thruster firing. And this I have put the GSAT-9 satellite which we have flown. And now, as I told, the material indigenization, everything is carried out, completed, and we do the plasma modeling also. This is also a little complicated because with the plasma modeling only, we can evaluate the life of the thruster. Because with the plasma modeling, we evaluate how the liner will be eroded and the shape of the liner and how long will it take for the liner to erode. And with an estimation, we'll be able to tell how long the thruster can work perfectly. And I told already about the diagnostic system. These are all indigenously made by ISRO now. And we have also the testing facility in ISRO. Now, this is the development cycle we have gone through. We have different classes of thrusters. We have 18 millinewton thruster, and it requires around 350 watt. So it was already demonstrated, as I told, in GSAT-9, and it was also tested for 121 hours cumulative. Now again, we have 75 millinewton thruster, which we have flown only 18 millinewton so far. 75 millinewton we have tested in ground up to this much hours. And we also have a 300 millinewton SPT, which is actually scheduled for an immediate launch. We have actually tested it cumulative for a 310 hours, and we have tested it in different conditions, and it will be soon flying in a mission. And this is a typical diagram of a schematic of EPS. Now I have explained about the thruster only, this portion which I am highlighting now. But actually in the electric propulsion system, it's little complex. It consists of so many elements here. Starting from the propellant storage, they will be stored in tanks. And from the tanks to the thruster, there is a series of valves and some flow restrictors and all that, which will control the flow to the thruster. Here, the propellant will be stored at around 200 bar, high pressure, and then actually it should be brought down to around 3 bar here. So it will be done in steps. First 200 bar will be stepped down to around 5 bar, with a pressure regulating mechanism. So as I told, we always look for redundancy. So we have an electronic pressure regulator system and a mechanical pressure regulator system parallelly. And finally, we have a fine control system with a proportional flow control system and a series of valves. And we control the flow to the anode and cathode. I have already explained there's an anode and cathode. In fact, in our thruster, we have 2 cathodes for redundancy. So the flow is controlled here precisely with the help of these valves and flow restrictors. So this is a mechanism in which how the EPS is operated. Now, how the whole system will be operated, it requires an intelligence for operating all these valves and all that. So we require a control unit which will actually control the operation of all these valves, and it will actually work on a closed loop based on the pressure feedback. All the opening of these valves will be precisely controlled. Now, these are some of the challenges which is involved in the development of EPS and the power units. First, I'll explain what is involved in the EPS. As I told, the low thrust, because of this low thrust, we have to develop innovative ways in which with lesser power, we have to generate more thrust that we have to generate, and we have to improve the efficiency so that here again the same thing, with lesser power, we have to generate more thrust. So that efficiency also matters in that. But in this endeavor, we should not lead to higher thrust, because then the payload weight will increase. So we have to aim for always the thrust to weight ratio at an optimal ratio, and the development cost also should be very, very low. Now, as I told, this is only the main thruster and the flow control elements and all that. But the thruster actually requires, as I told, the anode requires a high potential, and heater requires a high current. So there are different requirements of voltage and current for the different nodes of the thruster. But in the satellite, there is only a single satellite bus, maybe 70 volt or 42 volt. It depends on the class of the satellite. But then this single supply should be actually converted to different levels of voltage and current for the thruster to work. For that, we require some power units. So these power units, actually what happens is this input bus DC is converted to different levels of power. Now these power units, they should be highly efficient, because if it dissipates more power, then the satellite need to impart more power to the thruster. That is not possible, or that is difficult. So the topology selection of all this power unit is, topology is nothing but an arrangement of devices inside there's a schematic, which actually generate, I think power electronics people will be they will be able to understand it more. So topology is very, very important in the design of this power unit. And we actually control some 350 volts and 15 amperes of current in the satellite. So that much high voltage and current management should be properly done in the spacecraft. So that is a challenge in electric propulsion system. And also the modularity is very, very important, because we should be able to troubleshoot the system in ground easily by removing the all the modules easily and plug in back. So modularity is very, very important. And when we deal with such high current and all, of course, there will be a lot of thermal energy generated, and they should be properly managed. But here the challenge is that we don't have convection, we have only conduction and radiation. So the thermal management also get a little challenging here. And now plasma, as I told, is a different animal altogether. It is not like the normal resistive, capacitive or inductive load that we use in electronic modules. It is a totally different load, because when we switch on the plasma load, it takes a very high transient initially. I am telling just one example. For a 15 ampere load, when you switch on initially, it will take a transient of around 300 amperes. So your power unit should be able to support such high transient requirements. That is one challenge. Also, we all know that who are in ISRO knows that we have a derating criteria. Whenever device is used, suppose it has 16 ampere capacity, we'll always use it for 8 ampere only. Most of them will be 50% derated. So when we does that, the number of component increases, but then it should not lead to mass increase. So that is another challenge. As I told, we always look for redundancy and reliability. So we'll have multiple models of or modules for the same purpose. And grounding scheme is very, very important, because in this kind of power unit, the electrical bus ground and the thruster ground should be galvanically isolated. So the whole scheme should be based on that. And we actually break our head in this grounding scheme a lot to make it work perfectly. And of course, ease of production should be there, because even though the system is complicated, it should be easy to produce. Otherwise, it will lead to it will be difficult to implement in future. Now coming to the future, I've got it from a paper which said that by 2027, we can see $18.9 billion. That will be the final industry, the cost when we migrate to electric propulsion. Also, people are getting more and more interested in electric propulsion. They are doing more research on SPTs, ion thrusters. So that a lot of advancement is staying in technology. And because of its high efficiency and sustainability, and because it reduces emission and it doesn't have any greenhouse gases and doesn't depend on fossil fuel, it has a bright future ahead. Also, there's increasing demand in communication, navigation, space exploration, and Earth observation also. So this is my final slide. I just read out, despite all the challenges which I have told you, electric propulsion continues to advance and is being increasingly used by a variety of missions. Also, research and development continue. Many of these challenges may be addressed, opening up new opportunities for electric propulsion in the future. Thank you so much for patient listening.
Thank you, Manju ma'am, for giving such a wonderful session on this electric propulsion.
You're not audible.
Hello? Hello?
Sir, your voice was
Am
breaking.
I audible?
Now all right, Mash.
Yes, sir.
Now all right.
I am outside, that's why I'm engaging in this. And I invite Calicut sir to make a comment on this program. And I invite Calicut sir. Welcome.
Thanks, Shajil Mash. In fact, today is a significant day in our Space Club's webinar history, the 56th session has very many specialities. One itself is, we have been not having much of a discussion on a emerging area of ISRO's new path, new roadmap, and this electric propulsion is one such area, I believe. And we are having for first time this kind of a topic has got into our mind of a students in a basic from its basic structure itself with the processes and all that. From that point of view, it has been one of the significant thing for us. And secondly, Dr. Manju has taken exceptional care to do it for the taste of the students, for their understanding. She has gone into the basics, the principles, theories, and all that into it. Iron propulsion to the electric propulsion and all that thing. So that way, it has she has brought a new kind of a cover for students to get into the inside well. And this we had the International Women's Day this week only, and she was very active in one such program also. She told me, and we are very fortunate on this International Women's Day time, we are able to get her. And our new thing is the co-hosting system. We were hosting ourselves. The UL Space Club itself was hosting so far, and now we have a partner in this time. The partner is Silent Valley School, and the principal has spoken very well now in the beginning of the program, and we thank the school for being the co-sponsor this time. We are expecting many more schools to come forward to take the responsibility of sponsoring our program, and through that to empower their students into the area of the high technology area of space science and technology, space science, not only space science, science, engineering, technology, and mathematics also. So this is a process which has started now, and I understand a lot of veterans of ISRO have come and listened this topic. The topic is of a very significant thing. It's a new technology, continuous explorations program, indigenization efforts, different processes involved in this technology realization, proving it, testing it, and things like that. So lots and lots of areas are covered in this talk. I don't want to get too much into this, and I want the students to interact with our speaker and raise their doubts. And in science, the main thing is questioning. She has spoken about certain basic things. You please find out what you have understood and what you have not, and what you want to know more than what Dr. Manju has explored. So you please, I don't want to come between the students and our speaker, but at the same time, I also want our veteran ISRO people like Dr. V. Jayaraman, who was the director of NRSC earlier, and Papan, the mission analysis fellow of spacecraft, expert in flight dynamics, and I think many more people. And I would like them to make a comment before it starts with the students' interaction. Varun? Hello, Varun.
Yes, yes, sir. Yes,
Please
sir.
take over. Please take over.
I invite
Hello, sir. Shell, sir.
I invite Jairam sir to make a comment, and the students be there with your curious questions. You will get the time to ask these questions. I invite Jairam sir. Jairam sir is there, and Nagaraj sir, and Padmanabhan sir.
Oh, Dr. Nagaraj is also there. Eh?
I invite all the veterans to make a reflection on this wonderful technology.
Dr. Sundarajan is there.
Person from SAC. No, sir. One more person from newly has come. That is Kishore Kumar Barucha. He is also joined with us this time, first time. I invite Kishore Kumar. Welcome.
Yes, sir. I am Boru Chabam, second Ahmedabad.
Excuse me all.
Yes, Adil, you can ask the question in the questions. The questions.
Adil, wait there. You will get a chance. Wait there.
Okay.
Hello.
Yes, sir, you can speak now.
I just wanted to find out what is the maximum impulse that you get from this type of 300 milliwatt thrusters that we have made, 300 millinewtons thrusters that we have made.
Shall I answer?
Yeah, please.
Yes, sir.
Yes, sir. You are asking about the indigenous thruster we have developed, right? For 300 millinewton thruster, we have achieved around 2000 seconds specific impulse.
Okay, thank you.
Thank you, sir.
Hello.
Excuse me, can I ask questions?
Yes,
Adil,
Prajeet.
In a plane, four
Pardon?
motions. In the moving of a plane, four motions are there. There is lift, drag, thrust, gravity or weight. I can share my screen.
Yeah, sure.
No, please. Okay.
The thrust moves, pulls or pushes the planes to front forward, and the drag is the atmospheric resistance that push or pull to backwards. And the lift pulls upwards to the plane. Gravity pulls downwards to the plane. This is why the plane stuck for some seconds in the land. But sometimes the thrust have high power and the drag have low power, and the lift have high power, the weight have low power. You got it?
What is your question?
But in a rocket, where is the drag and thrust?
See, there is a basic difference between aircraft. You are asking about aircraft, right? So aircraft and rocket. Aircraft actually remains in the atmosphere. What you said is correct only. And you know Bernoulli's principle. As velocity increases, pressure decreases. So there is actually a difference when the aircraft flies. There is a difference in the pressure between the upper surface of the aircraft and the lower surface of the aircraft, and that is why the aircraft remains floating in the atmosphere. Actually, the engines of the aircraft doesn't have any work on this. Actually, they only help to propel it forward for the velocity or reach your destination. How it keeps floating is because of this difference in pressure, and you know the shape is like a teardrop. So it is, if you see the aerodynamic structure, it is made in such a way that the pressure is higher at the bottom of the aircraft, and the at the top of the aircraft it is lower. That is, it keeps pushing up the aircraft and it remains floating. Now, coming to rocket is actually, going straight upwards, and it is breaking the atmosphere, and definitely it has got so much of drag and all that, but it overcomes all that, because it also has an aerodynamic structure which overcomes all this drags and all that. But as I told, it has a heavy initial thrust it gives to the rocket, so that it takes lift off with all this thrust and goes straight up, and then only it gives the lateral motion when it reaches that particular orbit. So actually, whatever you are asking about the aircraft and the rocket is a slightly different technology.
Okay.
Hello,
I think
are you clear about it? May I know your good name? Who asked this question?
Adil Prajesh.
Adil Prajesh. Okay. Elatur.
Yes. Yes.
Okay.
My
Thank you, Adil. Thank you, Adil.
Thank you, Adil.
okay.
How old are you?
He
I
is
have-
in sixth. He is in sixth standard, and
Oh.
in a village school.
Oh, Adil, congrats to you thinking like this. I am so, impressed by your question.
Normally our students are from 8th, 9th, 10th and all that. He is an exception.
Nice, Adil. Keep it up.
I have another doubt.
Please ask.
Vulcan is a planet. It was a theory between Sun and Mercury.
Which one?
Vulcan.
So?
But it is a theory. In this time, that everyone realized that there is not a planet named Vulcan. This is right. This theory is right.
Oh, actually, I'm so sorry. I'm not aware of that. I will not answer any question. Maybe, sir, Jairam sir, you can tell on that.
I don't know. I'm not at all involved in this kind of thing.
I also
nothing like a
don't know,
Vulcan.
Manan.
You said theory is not at all existing. Okay, there is no planet that way.
Yeah, that only I know, but not aware.
I see this.
Maybe
I see this YouTube channel
false concept.
Adil, we will discuss it separately. This Adil is a astronomy buff. He is very excellent in that.
Maybe one more second we can ask him to talk on the topic. Very nice.
Keep it up. Keep it up.
Okay.
Thank you.
Okay, thank you. Thank you, Adil.
Now we'll go to the next student.
Yes, then Varun, please proceed with the question answer session and invite the students and those who are. You can ask any question. Okay.
Yes, sir.
Adil
Neela is
ready.
here to manage the question answer session, sir.
Okay, welcome Neela, who is a student from Alapi, and he will lead the session. Welcome, Neela.
Okay, so our session is over. I know a lot of the audience have several questions related to the topic, electric propulsion. So we received a couple of questions in the comment box. The first one, Kamya can ask her doubt. Is she in the meeting?
Yeah, I'm there.
Okay, you can ask your question.
Greetings of the day, ma'am. It was a great session. I had this question that what is the greatest obstacle in generating the thrust from the electric propulsion? Like, why is the rate so less? We could develop from 500 watts to 5,000 watts only despite, 1970 to 2020. So what is the primary reason behind it?
So I think there are two parts in your question. First is you are asking why it is low thrust, right? And then we are asking why low power. Okay, because these are two different things. Okay, I will address it separately. Why low thrust means because only ions and electrons are involved, and the mass. Even xenon has an atomic mass 131 or something. So it is so small, so we can generate only small amounts of thrust. But still, we are exploring many new technologies wherein we can use the same or harness the same technology for higher thrust. That is one thing. Secondly, you are asking about the power. As you rightly pointed out, see, how will you get the power in a satellite which is in space? Either wind or solar power, right? Mainly solar power. So for solar power generation, we require solar panel, and we cannot carry huge, big solar panels out in the spacecraft. It will amount to the weight, and there's a technology involved. So there is a limitation on how much we can harness the solar power. So we are working on that, and that has improved over the years, and that's how I showed the slide also. So it has improved over the time, and we have reached up to 5,000. Maybe in next few years we'll increase that. There's a possibility. Yes.
It is Neela, isn't it? That question is asked by Neela.
Neela. Kavya.
Oh.
Yeah.
Thank you, Nila.
No,
Nila is our discovery from Trivandrum. In our camp last year in Trivandrum, we had a 3-day residential camp, and there she came and attended. And thank you, Nila.
I think the question was from Kavya, right?
Kamya.
Nila is
Kavya.
handling the question session, and Kavya asked
Okay.
this particular
Okay.
question.
Thank you, Kavya, for the
Oh,
question.
Kavya. Okay. Kavya is different. Okay.
Yeah. Nira was handling the session. Yeah.
Okay, next, Suryajit Suresh can ask his question directly.
Hello, ma'am.
Yes. Suryajit.
Am I
Hi,
audible?
Suryajit. Yeah.
So my doubt was regarding the erosion of the thrust component of the electric thrusters. You said that as the shape of the thruster changes, the shape of the magnetic or electric field also changes, right?
Yes. Yes.
So does that in any way, either in a small way or a large way, affect the internal components inside the satellite or the thruster circuitry?
No, it will not affect the thruster or the satellite as such. What will happen is that I told you how it works. So the electrons should get trapped in that magnetic field, and that should ionize the incoming neutral propellant atom. So what happens is that presence of that electrons and they should be in cyclotron motion in that particular discharge channel. Discharge channel is only 1 to 2 mm width and all that. So the electron should be present in that particular area for all operation to happen. Now, what will happen is that suppose the liner gets eroded and magnetic poles are exposed. What will happen is that magnetic field shape will change. Now the electrons will not get trapped in those particular area and will not get the ionization as we expected. Now the efficiency of the thruster is directly related to the ionization efficiency of the propellant. If it doesn't happen, it will affect the operation of the thruster and will not get the operation what we anticipated or envisaged. The whole mission is planned according to the thrust we are expecting from the thruster. So we will not get the thrust. That is the problem. Otherwise, no issue.
Thank you, ma'am. And if it's not a problem, I have 2 more doubts. Can I ask?
Please ask.
So earlier you said that even though with greater time we can increase the power output of the plasma generator, but can't we increase the thrust due to the increase in pressure of the generator?
I didn't get Mone. What was your question? Suryajit, can you please repeat?
If we increase the pressure of the generator, couldn't we get more thrust?
Pressure of the generator means which generator?
I couldn't get the word due to the fast ongoing slides, but what I was saying is that if we generate the plasma or the thrust component in high pressure, for example, the ions, if there is a high pressure involved, shouldn't we get more thrust?
Maybe Dr. Manju, you mentioned about cyclotron resonators, no?
Oh, okay.
You can talk about cyclotron resonating, the resonation part of it. If you talk about it, you will understand better.
Okay, but what I explained here is here also the pressure is involved. Actually, because of the xenon pressure which we actually admit inside the thruster only, these ions get pushed out of that thruster and all that. But in the particular class of thrusters I talked about, here pressure doesn't have much role. Okay,
so we can't use any pressure to increase the thrust, or the pressure is actually useless in this process.
In this thruster, yes. Maybe we can explore the possibility of that in different kind of thrusters as Jaran sir was telling.
Okay,
you can talk about throughput also. Dr. Manju, you mentioned about throughput considerations, you may understand better.
What is
ISP,
that, sir?
You mentioned about ISP, you mentioned about thrust, you also talk about throughput considerations, okay? The specification may be there for throughput also, no, for each thruster.
Okay.
So
Dr. Manju, can I make it simple? If we can increase the production of the plasma, can we increase the thrust?
No, it is not. Yes, in a way, yes, sir. But it is not enough that plasma is generated. It also should be expelled.
Yeah, that is what.
Yes.
There is enough
we are increasing the generation of the amount of plasma generation,
Yeah.
then it has to be energized and thrown out, isn't it?
Yeah, exactly, sir.
He's asking, with that process, if you are succeeded in accelerating the plasma material, can we increase the thrust? Is it directly, or how is it proportional to the generated amount of plasma?
Yeah, because the generation of plasma and the ejection of the plasma out of the thruster actually amounts to the efficiency of the thruster. So definitely, if we can increase the efficiency, if we can increase the ionization of the propellant, it can definitely increase thrust.
Okay.
Yes.
But if there is more plasma, your ionization process also should have a lot of work to do, right?
Yes. But actually, in the thrusters, we'll get around 55% efficiency only. Normally, in 300 millinewton and all that, we are getting 55 to 60% efficiency only. But maybe we should also work on or research on the possibilities of increasing the efficiency. Thereby, as he rightly said, we can actually use that same kind of power for higher thrust by improving the efficiency of the thruster. And also,
you ask him whether he is satisfied with his answer.
Are you satisfied, Suryajit?
Thank you, ma'am. And also, I couldn't get the question right because I am not very good with my way of asking questions.
No, it's
Not
okay.
good.
Okay.
Not good.
Very good. You are very good. How old are you? Which standard are you studying?
I am studying in 9th standard. I am 15 years old.
Very good. Very good.
And ma'am, I have a last doubt also.
Yeah.
Yeah.
What is that?
During the testing of plasma thrusters, does any accidental faults may be potentially dangerous?
Of course, all the tests are hazardous. We take utmost care while we test it, because even it is tested in the vacuum facility. We have, as ISRO, all the sirs here know, we have a different levels of reviews. Our pre-test reviews and all that, then only we go for the final hardware test. Fortunately, we have not faced any problem so far. We take the utmost care while testing, because it is tested in that vacuum facility, and we are dealing with high voltage, and particularly not even during testing, when we are dealing with the power unit. I told you we are handling 350 volt and 15 amperes of current. So there also we take utmost precaution in doing designing and while testing also. And we actually test all these power units in ESD tables. You know that electrostatic discharge can happen. So we take utmost care in testing only in that ESD tables with proper gloves and proper precautions. Yes, everything is done with utmost precaution.
Thank you, ma'am.
Thank you, Surajit. Surajit is one of the top-ranking questioner. He asks very interesting and deep questions normally.
Yeah, because I am so surprised, because nobody asks about test and all that. So he is actually at 15 years of age, he is asking about testing. Nice.
Ma'am.
Yeah.
I wanted to ask, have you been personally attended or been involved in making or testing of such electric thrusters?
Mone, I am the project director. I am doing my job. I get salary for that.
Ma'am, I am not talking like the giving instruction or checking out the materials type. I am asking
hands-on.
Hands-on. It is hands-on. Hands-on.
Okay, Mone, I am basically electronics engineer. So I have done hands-on in the power unit. Okay, because I've grown up like that. Now I am in a little higher level management. So I'm not doing hands-on job anymore, but I am overseeing everything. Okay, so I've seen all that, but there are other people to do that work.
Thank you, ma'am.
Thank you.
Okay. Yes, dear students, while you are asking the questions, you will self-introduce yourself. Then which school, which standard, that would be good.
Yeah.
Okay. Okay.
Excuse me, ma'am.
Some with okay. Ask this.
Can I ask?
Yeah, sure.
Ma'am, my name is
My name is Punya and I'm studying in 8th standard in Spring Valley School. My question is that can we use like you have mentioned that we will be able to see many more development in this sector by 2027. And my question is that can we expect development in such a way that it will be useful in our daily life too?
Daily life.
Yeah.
Basically, these thrusters are operational in vacuum. So how will it be operational in daily life? Maybe, but definitely, this is mainly used in now automobiles, like Tesla has already done with electric propulsion, and also an aviation. I think one Israel company, they have flown with electric thrusters in aviation. Likewise, we can find out some innovative ways of doing implementing it in our daily life also.
Ma'am, can I also have one more doubt? Can I ask?
Yeah.
Ma'am, we will see many modern techniques in the field of medical equipments for like many diseases like cardio diseases, and we have seen the usage of artificial heart nowadays.
Heart valve
And yes, ma'am. No, providing artificial hearts help for the person. And my question is that while modifying this method, can we use it as for such medical equipments while modifying these?
This gives me some idea. Let me think about it. Thank you. Nobody has thought about it, but definitely I'll give it a thought. I don't know. I will explore the possibility only.
Thank you, ma'am.
Thank you.
Aditya Gopal raised a question on the comment section. You can ask it directly.
Yes, Aditya.
Am I audible, ma'am?
Yes, yes.
Good evening, ma'am.
Good
My
evening.
question is, we are using the xenon gas as propulsion, the fuel, right? So,
yes.
And the xenon gas, I think, is too expensive. Can we use any other type of gases like iodine or something?
How do you know
More
xenon is so expensive? I'm so impressed.
I don't know. I just Googled it and it showed that
Google.
Google.
for a bottle of xenon, it showed some sort of $1,000 or $10,000 for a bottle of xenon.
Exactly. But because it has so many advantages, like its ionization potential is very low, its atomic mass is very high. So that is why we are using xenon. But definitely, as I told, no, SpaceX has used argon, which is the nearest atomic mass, and I showed now music has used so many other gases. But yes, we are planning to get a strong hold on xenon. Then we'll gradually migrate to other gases also, maybe argon or something we'll also try, because as you said, xenon is exorbitantly priced. So we are also facing the same issue. Nice question, Aditya.
Okay,
thank you.
Okay, thank you, ma'am.
Aditya, where are you from? Which school?
Actually, I'm an engineering student, second year, CET.
Where? NIT?
No, CET.
CET Trivandrum. Okay, good.
Oh, my college.
Your college. Yeah, that's right.
Aditya, you can ask your question.
Good evening, ma'am. I'm a 6th grade student from Devgiri CMI Public School. I'm Adidev. And my doubt is that you mentioned that many fuels are used for electric engines, right?
Yeah.
So is there any difference in the thrust or ISP of a particular fuel in every engine, in an engine?
I didn't get that. What is the doubt?
When different fuels are used in an engine, is there any difference in the thrust or ISP of the engine?
When different propellants are used. Is that the question?
Yes, ma'am.
Yeah, it will be different. It will be different for each propellant. That is why I told, no, because we are using xenon for its specific advantages. We will be migrating to other propellant also, and the different. But actually, it all depends on the mission requirement. What mission wants, so how much thrust mission wants. See, now we are discussing on some spacecraft where actually very low thrust, 1 millinewton thrust is only required. So that in that case, it's not a problem. So yeah, definitely to answer your question, it is different.
Madam, Dr. Manju, this Adidev is a 6th standard boy.
Wow.
And he was selected by us to take to Bangalore facility of for NIT is making a satellite. In the context of that, 4 students were selected and 3 teachers. He is one of them to go to Anand Technologies Bangalore to have a visit. Dr. Subbarao invited us, including this boy, and he bore the entire expenditure and all other facilities he provided to this boy and us.
Anand Technology is our regular, partner.
Yeah.
Staff. So I know Subbarao sir, and there is a facility in Trivandrum also. So it's very impressive, Aditya. What kind of satellite you are building?
Ma'am, I don't think we have completely decided on which type of satellite we are building.
That configuration process, etc., are going on.
I think ISRO is supporting for that, right?
Yeah, correct.
Which center? URSC or?
No, NIT is the lead place, NIT Calicut, and
which
IAS,
center?
we are in touch with IAST and all that. So it is,
okay, nice. Keep it up, Aditya. I'm so impressed. There's a bunch of very talented kids out here. Nice.
Thank you, ma'am.
Thank you. Congrats.
This boy met me when he was in 1st standard. I met him in somewhere in Calicut city in some program, and he came with mother, and that day onwards we are holding his hand.
I am just requesting all of them to please come to ISRO. Don't go abroad. Come to ISRO, work for us.
See, Adidev, see, you listen to that.
Okay, sir.
Thank you.
Kamya raised another question.
Yeah.
You can directly ask to ma'am.
Yes, Kavya.
When it comes to EPS and CPS, which is more reliable, like
reliability.
Yeah, like during a difficult in some kind of emergency or something, like which would be more reliable to use it for the people.
No, I won't compare it with respect to reliability because both are reliable. And it depends on the kind of requirement you are having. I told you that I gave you the comparison chart, right? So both are reliable and all that stuff, but it only the different some parameters are different. That's all. I already told you about. I will not compare it with respect to reliability.
Oh, okay. Thank you.
Thank you.
Hello, Varun. What next? Varun? Who is hand?
Nila?
Okay, Varun. Okay. Nila is there. Then is there any other student from Spring Valley School? Hello?
Sir, Jeevan Mathukutti, a 9th standard student, raised a question.
Okay.
You can directly ask.
Good evening, ma'am.
Good evening.
I'm Jeevan Mathukutti from Government Technical High School. I'm studying in 9th, and my classmate is the recently asked one, Suresh. We are classmates.
Very good. Okay.
Ma'am, my doubt is that can we use lightning as a propellant?
Lightning.
Wow.
You know how much voltage is required? I mean, how much voltage is involved in lightning? Can you tell me that?
It is high. With the necessary formalities, could we use it?
That is what you tell me. What is the voltage involved in a lightning?
Current.
I heard it has a very good thermal conductivity, and also it's hotter than the surface of sun. But could we use it in a very little manner?
That's what I told you, to harness this kind of high energy things, we need to acquire technology. So I told you, even with 350 volt and 15 amperes of current, it's very difficult. to find the proper satellite grade component. See, the challenge in designing for satellite here, Jairam sir and others will know, because it is easier to design for industrial grade or commercial grade package, but when it to come to satellite, the availability of components according to our derating criteria and all that is very, very difficult. So when we talk about this kilovolt range of potential and all that stuff, it will be a little challenging. So it's a different area altogether.
Can I come out with one?
Of course, sir.
Hello, are you talking about the lightning in the atmosphere that we say?
Yes, sir.
But lightning is happening around 2 kilometer, 3 kilometer high, 4 kilometer maximum between the clouds. But in the atmosphere, in the space, we don't have it, no? We are
Yes, sir.
talking about 36,000 kilometer away. You get a lot of plasma from the sun.
Also, we need to wait for the lightning to happen.
Yes, exactly.
Sir, could we create thunderclouds there?
Everything is in the atmosphere, only beyond the atmosphere going on. No? Dr. Manju.
Yes, yes, sir.
One thing you can probably elaborate to other people also. All these technology, techniques, etc., we talk about in all the orbits, what you mentioned, whether it is low Earth orbiting or a medium Earth orbiting or a stationary or a geostationary orbit, even solar systems, all right. But if you want to go to interstellar media, interstellar space, electrical propulsion system is currently not really viable. Okay, maybe you can comment on that sort of scenarios. What will happen those days? How to control that?
Sir, in those scenarios, as you rightly pointed out, we cannot depend on solar energy. There we have to resort to nuclear propulsion. Okay, currently we are actually working on that. We have a project here in LPSC where we are working on that. So here nuclear energy will be used, but the problem is that the problems involved in the nuclear propulsion, but definitely, it will be very interesting. In one day we'll turn to nuclear propulsion and we'll be flying with nuclear propulsion.
Exactly. I thought that will be an input for the students to understand what are the challenges.
Maybe yes, sir. But very nascent stage, so I didn't want to, put
for
that
them
on.
to take up an R&D tomorrow, okay, for them, in their future, okay.
Yes.
By the time
Definitely.
they grow up, maybe the technology would have grown.
Correct. It's good that you pointed out that, but I didn't put that because it's in very nascent state.
Okay.
It's good. Yeah, that is an idea. Yeah.
Varun, what next? Shajil Mash?
Sir, we have a...
Come on, Varun. Come on.
Sir, we have the webinar quiz after this session, so I would like to request Adil to post the link for that webinar quiz. There's only a few questions are there related to electric propulsion, and the students, participants can attend that quiz, and the first prize winner will get some prize from UL Space Club, and it's sponsored by Syndrome Nurture, which is a supporting group of UL Space Club, which is a supporting entity based on Calicut, Bangalore, and a few other places. So, Adil, I request you to post the quiz link.
And
So
what next?
you can attend the quiz only after the vote of thanks. So, with your permission, good sir, shall we move on to vote of thanks?
If there are no more questions, then we can.
Nila, is there any questions?
Nagulan raised a question in the chat box. It's your time to ask directly to the host.
Is he available? Nagulan, is he available?
Yes.
Then please raise your question.
Propulsion
Time is important, please.
So, I have this doubt whether electric propulsion has actually been used to send a satellite to space, or if it is still in testing stages.
No, I actually showed many slides. No, so many satellites from 1957 onwards till 2023 February. So many satellites have been. I showed a roadmap also.
Including Indian satellites.
In Indian, I
GSAT
already
9.
showed. 2017, we have put only one satellite, GSAT 9. That's what you asked.
Ma'am, his question may be like, does it used as a launch system for a rocket?
No, it cannot be used because we are talking in terms of millinewton thrust, and actually even all the launch vehicles have around 500 to 2000 tons. So it's really impossible to use as lift off mass. But of course, in satellites and outer space, where we are concerned about only the gravitational pull of celestial bodies and other astronomical bodies and only minimum drag, we can use. Otherwise, no.
Okay, thank you. Ma'am, before going to vote of thanks, let me raise one question, which is not directly to the theoretical part of this particular topic. But as of now, there are few other emerging technologies related to propulsion is also rising. Like a startup called Spinoff has made such a test flight, and a few other propulsion technologies are also emerging. So as a person who is working on electric propulsion, which is a modern technology, so how do you what's your point of view on these kind of emerging technologies other than electric propulsion in propulsion techniques?
Okay, currently I am heading a team for electric propulsion only. But as you said, I have also read like water is used, air breathing technology is used in electric propulsion. So many new things without zero propulsion. So many things are emerging, and we are also working on different variants of electric thrusters. But maybe somebody in ISRO will take up other kind of technologies also, because it's really interesting how the space industry is turning up. So hopefully, yes.
Yes, ma'am. Thank you, ma'am.
Thank you.
And as I already discussed with you in first meeting, we are trying to developing a project which is based on Faraday Cup experiment, that kind of thing. So we seek all your support and guidance for that particular project. It's a small kind of prototype development, and we would like to have your support throughout that program.
Correct. Actually, I will tell you this Faraday Cup and Langmuir probe, which I have presented earlier. All these diagnostic probes are developed. We are developing in collaboration with IAST. Okay. Yes. So I actually don't know how we can formally collaborate, but just write to me. I will get in touch with the IAST personnel who are in charge of that, and I will let you know. Okay. Drop me a mail.
Our requirement is basically. IAST is ready to support us because I was discussing this with YVN Krishnamurthy sir, who's a registrar, and he's ready to support us. But we would like to get support from some resource person who is expert in this topic, Faraday Cup experiment related.
Definitely, there are some resource persons who are expert in that, and they are developing all this. And I told you we are implemented that also. There are persons available. But I am not sure how I will formally introduce them into this picture. But please drop me a mail regarding that. I will let you know.
Okay, thank you, ma'am.
Okay.
Thank you. Because it's a management question. I am not, I cannot answer.
Okay. It's a very, your response has been very nice, and we have also got a lot of encouragement and support from IAST also. I think we will try to go ahead. Thank you.
Sir. Whatever help I can, I will definitely do.
Thank you very much.
Good, sir. Shall we move on to vote of thanks?
Yeah, please.
Yes, Varun, we have Punya from Spring Valley School. They are our co-host, and she already posted her questions and introduced herself. And we invite Punya on behalf of Spring Valley School NIT campus to express vote of thanks in our 56th webinar. Welcome, Punya.
Thank you, sir. A very useful webinar for students was held on the topic of electric propulsion today, organized by UL Space Club. Certainly resulted in gifting us a lot of new knowledge. And I express my gratitude on behalf of my school, Spring Valley School and IT campus, to Sri E.M. Kutti sir, the founder and mentor of UL Space Club, Sri Shajil UK sir, moderator of this webinar, who addressed our webinar. I greatly thank our chief guest and the speaker of this webinar, Dr. Manju S. Nair ma'am, Project Director, High Trust Electric Propulsion, LPSC ISRO, who here opened up a new avenues of knowledge to us, the students in this webinar. I express my gratitude to Sri Varun sir and Jayaraman sir on this invaluable occasion. I also thank to all the students who participated in this informative webinar. Once again, I would like to thank on behalf of my school, Spring Valley School and ITC campus, as well as personally to all the coordinators for giving us this wonderful opportunity to be the co-host and to participate in this webinar, and to our respective speaker, Dr. Manju S. Nair ma'am, for your valuable time for spending with us by clearing our doubts and for giving us a lot of valuable information. And also to all the students and teachers who made this 56th webinar of UL Space Club a great one. Thank you.
Thank you, Punya. You have done it in a very good manner, and all of us are happy to from you. And the co-host system will continue. And Spring Valley School can continuously participate in all the programs, and you will get again your chance to co-host again after a few rotations. And with permission, sir, shall we wind up today?
Oh, we have spent more than an hour and almost 50 minutes. It's something so fantastic, Dr. Manju. You have been so nice to our students and us. Thank you very much.
Thank
And
you so much.
Jairam,
It's such an honor and pleasure for me. Thank you, sir.